Here. Okay, so the question by your colleague is about this structure, which was not given during the usual written exams, was probably treated by Maria Chiara while she was doing the tutorial pre-course, okay? And such a structure, for example, is typically used to illustrate concepts like equilibrium and internal forces, okay? Why? Because it's a statically determinate structure, and you can tell that by looking at the fact that it's basically one single beam, although with a strange shape, because it's a U, and then something connected here, and it's restrained to the ground by means of a roller and a hinge. So basically, if you do the count, which is something I discourage you to do, but in this case I will do that, it's 3 degrees of freedom, translation, translation, and rotation, with 3 restraint degrees, okay? 2 here and 1 here, okay? So we are able to prevent all the rigid body motions of the structure. Question of your colleague is, if I have to determine the reaction forces, which are clearly HA, VA, and what's the name of this one? VB. I will call it VB. VB. How do I decide on the direction of the arrows? Which means, how do I decide on the sign of the reaction forces? Did I get it right? Okay. Tell me.
We choose our convention?
Yeah, how do I decide whether to put this arrow to the right, to the left? How do I decide on this arrow whether to put it upwards, downwards, and same for this one?
Is it supposed to not matter? Because in the end, if our answer is negative, we're just gonna realize that our direction was incorrect.
Yes. The direction you decide a priori, as Rima pointed out, is totally irrelevant in the sense that you assume a certain direction, which means by pointing this arrow to the right, I assume that HA is directed to the right. I solve with equilibrium equations. If I get HA positive, it means the direction is right. If I get it negative, it means HA is directed to the left. Okay? So convention is totally arbitrary. You can choose whatever convention you want. And then looking at the solution you get, you can reverse the arrow to match the correct direction. Okay? As a matter of fact, whenever you're faced with signs, it's always a matter of convention. It's the same with temperature. It was never somebody back some time ago decided that there was a 0 degree point, which is basically when water freezes, and that what is below is minus and what is above is plus. But there is also another scale of temperature, which is the Kelvin scale of temperature, where 0 is minus 273.15 degrees Kelvins. And so temperature is always positive. So it means that now in this classroom, we have something like, maybe it's 25 degrees, no, it's 20 degrees. It means we are in a classroom where the temperature is 293.15 Kelvins. So it's a matter of deciding a convention, okay? Now, of course, I assume you're not satisfied with just this answer, so we're going to solve the structure and to prove what I mean, okay? First by equations, and then by looking at the structure, okay? Clearly, simply looking at the structure, without doing any calculation, we have 1 and 2 vertical reactions, and we only have 1 horizontal reaction. The structure is subjected to 1 horizontal force which points to the left. What do I expect? I reasonably expect that this HA will counteract the applied force, and since this force is directed to the left, I expect this to be right, to be directed to the right. To prove it with equations, the equation I have to write is Rx equals 0. So I impose that the horizontal translation is not possible, which means the summation of all horizontal forces, or sum of all the components in the horizontal direction, should be equal to 0. Each component or force with the correct sign, okay? So, PL to the left, take it positive. If PL is directed to the left and it's positive, then HA, which is directed to the right, is negative. And this immediately tells you that HA is equal to PL. So this result tells you the magnitude of the reaction force, which is PL, and the direction. Since the sign is positive, the direction of the actual reaction force matches with the reaction force I assumed. So I can simply replace this HA by PL. And it is plain to see that the structure is in equilibrium as regards the horizontal direction. Then I have to work out VA and VB without any calculation. There are no vertical forces on the structure other than VA and VB. They both point upwards. If they are both different from 0, the structure would move in the vertical direction. So before doing any calculation, I know that if one is positive, the other will be negative, in order for them to counteract each other, okay? What's the solution for this? Basically, VA upwards plus VB upwards equals 0. From here, I go nowhere because this equation has two unknowns. One equation for two unknowns is not enough. I need another equation. Okay? What is the best choice?
Moment. Sorry about that. Going to the two forces.
Yes, but one is known, so a priori, your solution, your answer is right. You're on fire this morning.
No,
Tell me.
I want to be on fire on the day of the exam.
I wish so. Yeah, I mean, the idea is whenever I have unknowns, VA and VB are unknowns, choose a point where one unknown does not contribute. Otherwise, you have all the unknowns in one equation. It's not convenient. So the best choice would be either here or here. And as Rima pointed out, if I had started from the moment equilibrium, this would be the best choice because I would put to zero the contribution of this and also the contribution of the horizontal force had it been unknown. Noteworthy, this point also allows you to get rid of this contribution because the line of action of this force goes right through that point. Okay? So that's a wise choice. MA equal to 0 means VB times L divided by 2, which is clockwise. If you use this as reference point and you look at this force, it's clearly clockwise. Okay? Can you see that? Okay. And then, careful, because in this exercise there was a peculiarity which didn't take place or didn't occur in the usual written exams. There is a concentrated moment, okay, which has to be taken into account when you write equilibrium equations. Of course, it does not contribute to the translation equilibrium, but it exerts its role, it plays a role when you write equilibrium equations. This PL square is clearly counterclockwise. And it is always present in equations, regardless of the reference point you use. So if you write the equilibrium equation with respect to this point, to this point, to this point, and also to this point, it always plays a role, which is constant and does not depend on the reference point you choose.
How does that exist?
Sorry?
How does that exist?
A PL square
Moment, like inherent.
it can be representative of, for example, could be some heavy machinery with a rotating device which exerts an action which goes like this, which would then create a certain concentrated moment, or it can be representative of another part of structure which basically transmits a concentrated moment to this part of the structure. I will now show you an example of what I mean by looking at this part of the structure. Okay? So this is 2PL. Which means VB is correct. Okay? And to get VA, I go back to the previous equation. So VA is minus, which means the sign is wrong. So I reverse the arrow and I write the magnitude with positive sign. Okay? Now look at the structure. We have here a PL square moment which rotates counterclockwise. Okay? It's like when you do this, okay? When you take a pencil and you do this. It's a bending effect, rotating the structure, leading the structure to rotate counterclockwise. This is counteracted by a couple of forces, 2PL and 2PL, equal in magnitude, opposite in sign. Their lever arm is L divided by 2. So 2PL times L divided by 2 gives you PL square clockwise. Okay? Got it? Now, just to point out one very important concept. Forget this. And suppose that after writing this equation, I had gone directly to this one. To get VA, I could write another equation. What would that be? It would be, for example, MB equal to 0. Or, as you pointed out, it could be M with respect to this point equal to 0. The computational effort would be the same. This would not contribute, this would contribute, and all the others would contribute. Okay? Let's see what happens with MB equal to 0. MB equal to 0 means I have PL square, which is counterclockwise. I have VA 2PL, which is clockwise. So minus 2PL times L divided by 2. That's the lever arm. Always measure the normal to the force with respect to the reference point. Tell me. You have to speak up louder. I can. Yeah, we don't know. We don't know this one. We know that one. Yes. I already saw. No, sorry, I got it. Yeah, no, it's correct. Ah, yes, yes, of course. You're right. This is not known a priori. Correct. Thank you. Minus VL times L divided by 2. Then what I have this PL, which is again clockwise. Its lever arm is 2L. Then we have this PL, which is counterclockwise, and its lever arm is 2L. So what I have is minus PL times 2L plus PL times 2L. Okay? Equal to 0. This cancels out with this, and what is left is simply PL square minus VA times L divided by 2, which gives you again VA equal to 2PL. This is to point out that when you solve for equilibrium of one single element, you only have 3 equations available. Here you have 4, but make no mistake about it, only 3 are independent, in the sense that you get nothing more from writing an additional equation. Basically, this equation and this equation tell you the same thing that this equation tells you. Okay? Should be negative. Why isn't it negative? Ah, yes, because it was pointed upwards. Yeah. Plus, minus. Okay? If you have a structure that is more complex and you have more than 3 reaction forces, as it was the case in this exercise, then you have to split the structure into different parts and write partial equilibrium equation on substructures. Now back, yeah, tell me.
You said the U is 1D, and I guess the column is another element. So that's 2 elements? Or 1 element?
No, there are no disconnections, so it's just 1B.
Yeah.
Another question about this. When you work out the internal forces, is it the same? So the direction of the arrow doesn't
No, the direction of the arrows don't matter. The important thing is to fix the conventions a priori and to stick to the conventions. Okay? As we always did, when I plotted the internal forces, I always made it clear whether axial force was positive compression or tension, whether the shear force was positive clockwise or counterclockwise. As for the bending moment, the way we plotted bending moment diagrams is to specify whether it is plotted on the tension side or on the compression side. Okay? Back to the question of Gabriel, which is interesting because it is difficult to visualize why there would be a concentrated moment at a certain point of the structure. Suppose that I break the structure by isolating that upper vertical portion on the left. Okay? So basically I split the structure like this. PL, and then the rest. Okay? How does this stay in equilibrium? Well, it is connected with the structure by a point which is here and here, okay? The only possible way to have this portion in equilibrium, since it is subjected to a horizontal force which points to the left, is to have a force which points to the right here at the bottom, because all the other points are free from loads. Okay? Now, if you look at this sub-portion, it is evident that it cannot stay in equilibrium because two forces are equal, but they have a distance, a mutual distance, which is the lever arm. So they will induce counterclockwise rotation of the structure. Okay? So the only way to keep it in equilibrium is to have, additionally to these two forces, a clockwise bending moment applied at this point, okay, whose value is PL times the lever arm, so PL squared. Okay? Now if I go and I want to study the rest of the structure, what is the way to take this portion of the structure into account? Basically to substitute these two loads, take them and put them here by respecting the principle of action and reaction. So, if this point on this left portion is subjected to a horizontal force which points to the right, it means that this point will be subjected to a horizontal force to the left. Okay? Principle of action and reaction. And if here you have a bending moment which is PL squared clockwise, I will have here PL squared, which is counterclockwise. Okay? Principle of action and reaction. And then here another PL squared. Here the two reaction forces, VA, HA, and here you have VB. Now, I leave it to you. Try to solve this structure by neglecting this part and considering the two loads applied. Guaranteed, of course. This two forces, or this force and bending moment, that translate the effect of this portion of the structure. Just to quickly show you, what about HA? Do we have any other horizontal force other than PL? No. So you will surely get HA equal to PL. But let me just show you a moment equilibrium. I will write the moment equilibrium with respect to A. What do we have? We have VB times L divided by 2, which is clockwise. Then with respect to this point, we have PL times L, so PL square, which is clockwise. Okay? Agree? Then we have PL square, which is counterclockwise, and we have PL square, which is counterclockwise. Okay? Minus 2PL square equal 0. So what you have is VB times L divided by 2 minus PL square equals 0. And this gives you VB equal to 2PL. Okay? Got it? Honestly, you look more confused than before. But maybe you just need to think about it.
And this is slower than you are.
Okay, that's no
I have
problem.
a question.
Yeah.
Why is the moment that you do on that point over there clockwise rather than anti-clockwise? If you imagine this and you're pulling it from here and pulling it from here, it's rotating anti-clockwise.
Yes. So to keep it in equilibrium, we need it clockwise.
I just getting lost between when you are writing what's happening and when you are writing what's planted, what's happening.
Yeah, well, I didn't write the equilibrium equations in detail, but if you want to solve this one, you can solve it by drawing the load applied and then looking at the forces here. So basically you have an H, a V, and an M with signs that are arbitrary, not totally arbitrary. Do not think. I didn't think about them.
Okay.
Solve this substructure. You will get this one.
Okay. No, it makes sense. I just thought this is what's happening, not what's counted.
No, we are in the domain of statics. This you always have to be aware of. We are in the domain of statics. We are not covering dynamics.
I
So-
have no idea what the difference is.
The difference is that in statics, objects do not move. In dynamics, they move. So whenever you have a structure, whenever you have a sub-part of the structure, everything should be always in equilibrium, okay? So when I draw the free body diagram of the forces, which is basically this one, everything should be in equilibrium. So when I draw this moment, it is the moment that keeps the structure in equilibrium, not the effect of the forces applied. That's different.
Okay.
Tell me.
So in that case,
And speak up, please, so because I don't know whether the microphone picks it up.
when you break apart after you work out the internal forces like you just did, so in that case, you have to get the error pointed right.
No,
No?
no.
It still works if that H that you just wrote is facing the other way.
Yes, but that's all we said previously. When you have unknown forces, unknown means unknown, and unknown means in magnitude and direction. So you're not supposed to know the direction a priori. You fix an arbitrary direction, and you get the actual one by looking at the sign. As for the magnitude is a number, so basically it's calculations, you have to get it right, okay?
Professor, can I? Yes, I think.
Yes. Unless it's bad words.
Okay. It's a good thing you warned me. If this is like this, which it actually is, like, okay. And I want to do the same thing. Let's say I remove this and I want to write its effect here the same way you did. Would it be, there has to be one here and one here, and wait, what's going on? And this?
No, because you jumped one step. You marked here on the left portion the forces that act here. Look,
Oh, okay.
you see VA, HA require whatever the length of this, HA here and VA here. Okay?
Yeah.
So this is in equilibrium. And then since we have
Wait, so it's, how is it an equilibrium?
this one, look at
If
it.
you have, yeah, no, it's rotating like this.
Yeah, then the bending moment.
So
First
I
the
have
forces.
to draw a moment
HA,
for it to be
yes,
an equilibrium.
HA,
Okay, so
clockwise.
It's gonna be
it's gonna be counterclockwise, and its value is HA times what is the length? L.
So you're saying that when I take this here, it becomes the opposite?
When you look at these forces here, they are exactly the opposite. So it means HA, VA, and HA times L. But it makes sense if you think about it. If you push this at the top, what will it do, this member, on the rest of the structure? It will push at the bottom.
Yeah.
What happens when you have a column which is subjected to a load, a compression load? Will it compress the ground or will it pull the ground? Clearly. And this you get from this. Looking at the member, VA is downwards, VA here is upwards, which means when you take it and you reverse it, it becomes downwards again.
So for the horizontal and vertical forces, we're transferring them as they are onto the point.
I don't want to.
Say it like
I
that.
don't want to second this message. I just want to say
Generally speaking,
apply the principle of action and reaction. Because if I tell you this, I'm sure that sooner or later you will do what? You will forget this bending moment. Believe me. Fail is where good.
is there a way for me to assume the direction without doing that process, the direction of rotation?
No. Do the calculations and deal with it. Veronica,
Agree.
it's okay.
Good memory.
You're like the children I never had. So.
Except you do have a child.
Yeah, but I could have had more and more. So basically, my students are like my children.
Are you?
You are. And if I fail you, it's because of your own good. Believe me.
But
What an act of love. Can you imagine?
very grateful.
Tell me, Gabriel.
I don't understand where you got -2PL squared in the formula at the top, right?
Minus 2pl square, this and this. If I write the moment equilibrium here, now it's a little bit messed up. Rima messed it up.
Sorry.
Okay? But if I write equilibrium here and VB clockwise is positive, then PL square and PL square, which are both counterclockwise, are negative. So the sum of the two is 2PL square. It's minus PL square minus PL square minus 2PL square.
They're independent of
Lever arm and distance. Their contribution is a number. When you have a bending moment, a concentrated bending moment applied, its contribution does not depend on the distance from the reference point. It's always the number with its direction.
The reference point is at the top right. How did you get VB?
L divided by 2?
Yeah, it's
No.
3.
No. The distance is measured normal to the force. So the line of action is this. The distance is this. It's always like this.
Yeah, I always get confused with this as well, especially on picks like this.
But that's a basic rule. You don't have to overthink it. It's the rule. How do you calculate the moment? It's the product of the force times the lever arm. How is the lever arm defined? It's the distance between the reference point and the line of action of the force. And when I say distance, it is intrinsically defined as the shortest distance, okay? When you have, it's a geometric definition. How do you calculate the distance of a point from a straight line? It's the definition. Normal to the line. That I cannot give you some explanations, like yes. That I cannot give explanations. It's the definition of moment. The moment is the force times the lever arm, and the lever arm is the distance between the reference point and the line of action of the force. No mistake about it. You okay with everything? So shoot a question. Sorry. Yeah. Nothing to think about.
Can we ever do something with internal forces?
Yeah, let's make some observations about internal forces. We could do this one, but before I do it, note that this PL square and PL, which I then replaced on the structure, are internal forces. Are we okay with that? So when we now plot, and I will do it as an exercise, this does not reflect a typical written exam. Why? For two reasons. Because it's too easy. No, it has some peculiarities, but I don't like structures with fancy shapes. I prefer structures which reflect something that you could find in reality, and that's basically what you see when you look at written exams. We have simple geometries. It's nothing weird, but to make exercise and to, for example, plot internal forces, this is a good case. Although with an exception that I would like you to underline with red, okay? Now, underline. I usually don't give concentrated bending moments as a standalone force because it's difficult to visualize them in reality, okay? They are like a limit condition of something else, or as I try to explain by taking this portion away from the structure, they reflect the action of another part of structure. So, okay, why not to consider the whole structure? That's my point, okay? Want to give it a shot at the internal forces diagrams? No.
Sure.
Yes, but not now. First, I will introduce the topic. I will call you when I need you. Okay, I will leave that blackboard over there as it is because we need it. We need the reaction forces. But no. Vabbè. By the way, how is it going with Italian?
Non male.
Non male?
Sì.
Bene. And you? Are you learning? Non bene. Okay. Should learn. And how is it with campus life? I mean, now it's the best season of the year. Are you enjoying? Okay.
So
Yeah.
many things to enjoy.
What?
So many things to enjoy.
Yeah, and the weather is also quite nice, although maybe for May a little bit too hot. Especially in the central part of the day. But it's important, and try to learn Italian. It's a beautiful language. Okay, so problem at hand is to plot internal forces. Before even starting the calculations, let's think of what we are going to have. Okay? There are no distributed loads, as you see. Okay? No distributed loads on any part of the structure. Just concentrated loads, horizontal, vertical, whatever. Okay? Which basically means, what should I expect?
Which diagram are you talking about?
All of them. Actual force will be either 0 or constant along the members. Shear will be either 0 or constant on the members. So both actual force and shear force will either be 0 or rectangles, constant diagrams of internal forces. Bending moment will be either constant or linear. Okay? So your diagrams will look like what? Series of rectangles, or in the case of the bending moment diagram, straight lines. No parabola, or to be more correct in Latin, no parabolae, because it's plural. Okay? Parabolae. It's important. Got it? Second observation. Maria Chiara may have solved this by writing equations, correct? I will not do that. I will do it another way, to show you exactly that things can be done differently. So to give you more options when you are at the written exam. And make no mistake about it. I like this sentence. Make no mistake about it. The solution is correct when you have the bending moment, actual force, and shear force diagram correct. I don't care how you get there, unless you copy from your neighbor. No. Or you can also copy, but don't get caught. That's important. No. Delete it from the video. I didn't say that. It was just a joke. Don't copy. Copying is bad. Bad, bad, very bad. Okay? No, basically, all the solution is in the diagrams. And there should be a sketch of how you did the calculations, but also the other way, so not the way Maria Chiara does it, a more straightforward way, which is basically what I applied in the previous practical classes, if you listen close enough. So to focus on certain specific points, the most notable points, the most relevant points, and then to sketch the diagram based on a limited number of points. What I mean by that is, if you know the bending moment diagram is a straight line, you basically need two values. You don't need to have the whole equation. If you're sure about your concepts, and I'm quite sure, okay, about my concepts, basic concepts of structural mechanics, you don't need the whole equation, you just need to know some notable points, okay? Third observation, I will start from the left portion of the structure, just to show you that whenever you have a free end, and the point at the top left is a free end, where you know the load applied, and you have nothing else than that load applied, you don't need to know the rest of the structure. This is a concept which I show you. Why? Not because I think it's I don't know, a display of confidence with structures. It's because it helps you doing the things in another way, and especially since the first task of this structure was to work out the reaction forces, the left portion can be solved even without knowing the reaction forces. Its bending moment, axial force, and shear force diagram do not depend on the internal forces, on the reaction forces. Sorry. Okay? So I start off at the top. PL. What are the notable points I use to work out my reaction forces, internal forces? Again, axial force will be constant or zero. Shear force will be constant or zero. Bending moment diagram will be zero, constant, or linear. So the worst case, the more complicated case, is when I have a linear diagram, which only requires 2 points. Which means that if I have the internal forces here, I have everything I need, okay? So instead of working on a single element of the beam, the X element, the way Maria Chiara did it, so you have it in your solutions, I will look at the whole member. How do I mark the internal forces here? Now it's time to fix a convention. The convention I like is tension for the axial force, clockwise for the shear force. You see it? The member rotates clockwise. Tension means it's pulled, it will elongate. As for bending moment diagram, I don't need to place anything because I will plot it one way or the other and then look where the tension side is, okay? So now I take this. This would be the element for the conventions if the member was straight and horizontal. If it's vertical, it means I have to draw my conventions like this. I will simply rotate it by 9. Tension means this. Clockwise means this. Okay? If I'm at the bottom of the member, I am looking at the bottom face of the element. So, this is the shear force V. This is the axial force N. And the bending moment, I will fix it like this, M. Okay? Let's say prime, prime, and prime.
This a lot of the drawing is.
Based on what?
Yeah.
Based on what did I?
Draw the N and M.
N, axial force. V prime, shear force. M, arbitrary. Okay?
Are these things that are there or what are we doing here?
We're working out the internal forces on the left portion, upper left portion, at the bottom of the...
Working out, we are calculating these
Yes.
values. Are these values ones that we should already have from our calculations of
No.
equilibrium?
No.
Are we going to use the values we got from our equilibrium equations to do this?
Not right now. As I said, if you look at the left part of the structure, until you get to the center point where all the 3 portions get together, I don't need to know the reaction forces. And I dare you to prove me wrong in the sense that will I need to use the internal forces in this calculation? Clearly not. Because, yeah,
We're writing these to acknowledge that these forces and limitations exist on that point. But for now, we don't need to know their value. Yeah.
no, I mean, you can look at it the way you want. We want to determine the internal forces, we calculate them because we don't know them. It's a little bit philosophical.
But these don't influence our graph.
Yeah, of course.
Are these directions assumptions?
Are these?
The directions.
Yeah, it's assumptions. My convention. This is the convention. I mark this and this coherently with my convention.
And I understand that you're doing that based on this convention drawing, but why would you do that? Why would you write that when we can tell that the shear force is not going to go in that direction?
Because not everybody knows. Now we know, but if I give another exercise, maybe you don't.
But can you just infer from looking only at this that it's probably going to go?
Okay, then tell me right away. Will the actual force at the bottom be tension or compression?
What's happening on the reaction?
No. We skip the calculation. Forget all the conventions and tell me what we have at the bottom. Tension or compression?
I think the member is being compressed.
So who vows for tension? Who vows for compression by raise of hands? Compression, Rima. Tension, Gabriel. Who votes for zero actual force because there are no vertical forces applied on the member?
Okay.
Shear force. How is the shear force at the bottom of the left part? Clockwise, counterclockwise, left, right? Right. Clockwise or counterclockwise? Counterclockwise. It's correct. Well, how does the bending moment look like? Tension is on the left or on the right?
Wait.
Because that's we need to plot the bending moment diagram. Tension, yes.
Tension on the right?
Tension on the right. Yeah, looks like it. Okay? So you know the directions, but then you need the values. You need the values. So you have to work them out by equations. And when you work out by equations, it means you have to do the calculations anyway. So you can stick to a convention or you can change the convention unless you then, provided that you then can draw the diagrams correctly in magnitude and sign. Okay? Okay.
So we wrote the letters, the forces that are possibly there. And then some of them might not even be there. Some of them will be there, and we're still figuring out more direction.
Yeah, I mean, because now we are facing a structure which is quite simple and which, by the way, this part here, at least, I solved previously. So you know how the story is going to end, okay?
Yeah. Question. If this beam that we are discussing had a support, then it would be
Then it would be another.
Would it be compression?
Depends. How is the support? How?
But there is a force from this side. I know this is there.
But wait, because when we go to the right part, then there is an actual force.
Compression, right?
You will tell me.
I mean,
Okay, what are the equations in this case? Very easily. N prime equals 0. V prime is equal to minus PL. And M prime equal to minus PL squared. Okay? Got it?
Yeah. But I don't know if I can think of this in the exam.
Well, that's why I give you different options. That's one way to see it. Maria Chiara does it another way, different options. You simply have to choose the way to tackle the problem which suits you best. And maybe choose it in due time. Okay, let's go on. How can we now go on? Up to this point, it was easy. Now we have to go in the horizontal part. And again, I will do it another way. I will do it like this, by keeping also the vertical part. PL, my sign convention in this case is tension, clockwise, and bending moment, whatever. So, when I go to the point, sorry, this should be L divided by 2. So this is L divided by 2. I'm on the right portion of the member. So I look at this. There is a shear force here, V. There is a tension force here, N. And then a bending moment, which is M, like this. Okay?
Professor,
Yeah?
whenever we choose to plot our structure while calculating, we will always put these three variables in the direction of our convention.
Yep.
So even if I plot at L over 4, I'm simply gonna write all of these in the direction of convention.
Yep.
So it's not because this part of the beam is intersecting with the vertical part.
No.
Where
Unless, of course, for example, if there was a hinge at the right part, so if the left portion of the structure was connected to the rest by a hinge, I would know a priori that M would be 0. Okay? Okay. Again with the guesses, is N second tension or compression? So will I get a positive or a negative value?
tension. No, wait.
N second.
0.
0. Who votes for 0? By raise of hands.
No, wait, not 0.
Okay. Changing plans. You see, just it's enough. You see how you struggle by figuring out whether it's tension. And suppose if I asked you, what about the shear force? Is it right that way, so clockwise, or will it be counterclockwise? And what about the bending moment? It's not so easy to see a priori. Okay, I maybe can because I have not because I'm smarter than you, but simply because I have more experience. So I know that that portion of the structure is basically a cantilever, just a crooked cantilever. So it has diagrams which look like the cantilever with some changes. For example, what is the basic change in this case? If I write n second, the equilibrium for n second, what will it look like? N second to the right minus PL to the left equal to 0. N second equal to PL. So tension. And strange enough, it's the same value as the shear force in the previous case. Why? Because there is a right angle. So what is axial force becomes shear force and vice versa. So when I go into V second is vertical, nothing else, 0. Okay? But it's difficult to know beforehand all these things. The only way to do it, write the equilibrium equations. That's it.
Which be the opposite.
Yes, but I'm not seconding this.
Maybe because there's a support, so something should be different.
The only way to know is to write equations and to solve them. Face it. There's no easy way around. What about M second? M second is equal to what? Is equal to, this is clockwise, counterclockwise, this is counterclockwise, PL times L square. So in the end, you will have minus PL square.
Professor, when you're calculating this moment, okay, when you're calculating this moment, it's not about any point, right? About when you're about what point are you calculating?
Always about this point.
About the point where you got the answer.
Because otherwise, if you write it with respect to another point, you would have the contribution of this second and then the second. Okay? Got it? What I will do now, just to show you what we are doing and to go back into focus, I will now plot the diagrams for this part of the structure, okay? Just to show you where we get from doing this. So this you have now on your notes.
What are you gonna do now?
I will plot the diagram of the internal forces just for the left part, okay? And I will keep them. So, my way of plotting diagrams is I redraw the structure. And I start off by plotting N, whose convention is tension. Okay? What do we have in the first member? The vertical N prime equals 0. That's the way to say it's 0. Two architectural things, as AutoCAD calls them. Second part, the horizontal part, what do we have? N second equal to PL positive. Plus,
Does it matter if you draw it?
again, no, I'm not replying to this question. Because I replied it, I think, 1,000 times.
Doesn't matter.
Doesn't matter. If I say it's a rectangle, if I say plus, and if I say PL, that's all I need to know. I know everything. Okay? You can also, if you want, replace this by T, tension. Then I know it's tension. That's enough. Okay? Right part, we will see later on. Then, shear force. Clockwise. First portion is minus PL. Second portion is 0. So, rectangle here minus PL 0. Do they match with Maria Chiara's diagrams? You brought it up. You will check. I'm quite confident, but you'll never know. What? Ah, too bad. I think we have the tutorials on the Weebit. Ah. M I specify that I'm drawing it on the tension side. Usually when we do the exams in Italy, it's not requested to specify. but since I know that some of you come from the, I don't know, United States, Australia, other countries where the convention is the opposite, it's a convention, I don't care. Important thing you specify, okay? So I'm plotting the bending moment on the tension side. Here, I assumed tension to be left. What I got is minus PL square. So tension is on the right. Note that this value only takes place at the bottom. At the top, since it's a free end, bending moment is 0. So what I have is like this. Straight line. Then m second, I assumed it to have tension at the bottom. The value is negative, so tension is at the top. A quarter of circle, and then like this. And the only thing I need to specify is this value, PL square, because the direction or the sign is given by my convention, and the fact that I take this value and I bring it here immediately tells me that there is no discontinuity, so this value PL square is also this value here, okay? Now, let's look at the bottom stick, okay? So basically, what I'm looking at is this portion here, okay? Where we know we have, what do we have? VB equal to 2PL, correct? And then we have a PL square here. Okay? I'm now looking at the bottom part of the structure. In this case, I don't have a free end. The bottom end is restrained. So I have a reaction force. I need the reaction force to do my calculations. Okay? How am I going to do the calculations? As I said, the presence of the concentrated bending moment makes it a little bit more complicated than it usually is. More specifically, when you have concentrated moments, when you have concentrated forces in the middle of members, of straight members, it's always wise to consider what happens before the concentrated force and after the concentrated force, okay? Otherwise, you mess it up.
Are we going to split the beam plastic into two?
Yes. So what I'm going to do, I'm going to study the beam up to the point where the concentrated moment is applied. So imagine I'm getting the internal forces values at a point just before the concentrated moment and then at the top. Okay? These are the 2 points I'm going to consider for working out the internal forces. It's a vertical member, so again, tension for axial force and clockwise for shear. Okay? Bottom half, This is what takes place at the bottom. This is L divided by 2, but L divided by 2 means I get to mid-span, but I stop 1 inch, 1 millimeter before the concentrated moment is applied. At the top, tension is marked like this, and third, shear force is like this, V third, and then bending moment arbitrarily chosen like this. Tension to the left. What do my equations tell me? Simply that n third plus 2pl, they are both upwards, so the solution is n minus 2pl. What do I know from this?
Why minus 50? Wait, I thought it was in the other direction.
Okay. V third, the only horizontal force, 0. Moment, how is the moment?
Are we going to, if in this part of the beam, we stop right before P squared, and in the other part of the beam, right after P squared?
Not
do
right
I
after, not right after. At the top. Here and then at the top.
Will the other beam include 2P squared in our calculations?
Let's look at this first.
Because if neither of them do, then we just got rid of the moment, which is actually there.
No, I told you I stopped 1 inch, 1 millimeter before the bending moment is applied. So that's why I didn't mark the bending moment.
And I guess there is no moment.
Yes, your guess is right. But it's not a guess, it's an equation. You implicitly do the calculation and you conclude it's okay. Look at this. I mean, no other load applied than an actual force. What can the solution be? Actual force different from 0, shear and bending moment equal to 0. Exactly like what could happen in a truss member. In a truss member, that's the usual situation, just actual forces applied. Now, bottom half, entire member. So what I do is L, 2pl at the bottom, and pl square at mid-span. And I look at what happens at the top. Yeah?
What happens if I just take the top part of the beam of this number?
Let's do it. So just the top, you mean this one?
Yeah, but why did you choose to do the entire member the second time around? Why not just did the top, the bottom half, now we do the top half?
The top half, I think it brings confusion.
So how am I supposed to have the judgment to know that this time we do the whole member?
Makes no difference actually. But if I asked you, consider the top half, what would you mark here?
I will just say the same dot up there.
Okay, so actual force, 2pl, no shear force, okay, and then
And then I would put the moment,
which one?
P squared.
With what sign? Like that one or reversed?
I have absolutely no idea.
That's my point. To keep this, you have no doubts that the moment applied here will be the same as that, because I'm basically taking the structure out. If you go into such subdivisions, easily you will get confused.
So what is it supposed to be? In case I decide
No
to,
spoiler.
I mean, if
You
I,
have to think about it and then.
I don't know. If I just take the top half, do I need to reverse the moment? I do? I mean, reverse anything else. Well, not anything.
Who knows? Who knows? Let's solve it. N4 V4 M4. How do the equations look like? N4 equal to minus 2PL. Same. V4 equal to 0. Same. M4 equal to clockwise, counterclockwise, PL squared. Okay? So now we know that starting from this point up to this point, this is the situation. Whereas at the top, there is a bending moment diagram. There is a bending moment value, which is PL squared. Let's draw.
In reality, the moment doesn't just decide to stop at the middle of the beam, right? Like, I don't understand.
You don't understand.
Yeah.
Let's think about it in a moment when we have plotted the bending moment diagrams. What about actual force? 2PL, 2PL negative. So my diagram would look like, this is PL, would be twice as much. To draw it in scale, minus 2PL. Can you see, for example, can you see? This case, positive, I plotted it down. Here I plotted negative on the right. So it really makes no point. The important thing is to be consistent. So once I decide that the positive on a horizontal member is down, same should take place on other horizontal members, okay? Just this. V, 0. What about the bending moment diagram? I know it's 0 here. I know it's 0 one moment before midspan. And then I know that at the top, it's PL squared tension to the left. Okay? So it's basically here. What would it look like in the middle?
You have a triangle into the middle and then it's 0 along the line.
It's not a triangle because when you have a concentrated moment, it brings in a discontinuity and the jump in the bending moment diagram.
What's the triangle?
It is
But why did we start from the left?
where?
On the x-axis, like the horizontal beam. Why did you start the moment from there? Here.
We're not
Why
looking.
did you start from here? I mean,
It's a diagram. It does not have to do with this one. It's the diagram. It's the bending moment on this, and therefore it's plotted here. Its representation doesn't have anything to do with the horizontal beam.
confusing.
No, it's diagrams. When this is a diagram, it refers to this line. It does not refer to this line. That's the way diagrams are always plotted.
I haven't plotted that many in my lifetime, so I don't know.
That's why I don't like concentrated moments. As you see, it's more complicated. No doubt about it. Besides, as I said, they are also difficult to trace back to something that happens in reality. It's a limit condition. Okay? the top half.
I was like,
If you have this, no doubt there will be n third and v third, and that's correct. But if you have a PL square applied here, if there is none on the bottom half, it goes all on the top half. So what we'll have is that the PL square will be applied here. Okay?
is this our assumption?
No, it's not.
Then why do, who says there's none on the other half? What if quarter of it is on the lower half and the 3/4 is on the top?
But you cannot ask me who says there is no on the other half. I just worked it out. With equations, I proved that up to the point where the moment is applied, m is equal to 0. So this m cannot go to the other half. It has to go all on the top half.
These equations, we made them happen. M is equal to 0 because
We
we
did-
put the point of half a millimeter before.
Yeah, so no, we decided, we asked ourselves, what do internal forces, what values do the internal forces have here? Okay, that was our question. And we answered it by means of equations. So there are no assumptions of this. It comes from equations. Think about other examples.
So because of
No, stop. Think about this. Okay? Concentrated force applied on the half of a cantilever beam. Question to you. Will this force go to the left or to the right?
well, if you had drawn symmetric supports, I would say it would be
I
split
didn't.
equally.
I draw a cantilever.
I mean, I don't know what actually happens, but I'm assuming because the support is on the left, most of the force would be going toward the left because it is the only thing that can carry it.
Most of the force.
I mean, you can't exactly control where force particles go in the liar, can you?
No, in this case you can. In this case you can because if even a small portion of P goes to the right, who does counteract? Who keeps it in equilibrium?
The support.
No, to the right. I break the structure in two, okay? I consider the right half, which is L divided by 2. Here there is nothing, no load applied, no restraint force, no reaction force, no nothing. If there is, I don't know, this is P, let's say P divided by 100 applied here. Who counteracts it?
Professor, I understand the logic of it. I'm just trying to think of how it happens in real life. Like you have a beam and it has steel atoms. Like when the atoms on the right half are gonna be like, yeah, sorry, your problem. Only the atoms on the left of the beam will carry the.
But that's my point. You're trying to get the answer in an intuitive way. There is no intuitive way unless you have solved 700 structures, which you didn't for sure. I maybe did 666, the number of the beast, okay? Maybe. So I know for sure that this part of the structure has no internal forces, has no actual force, has no shear force, has no bending moment, simply because it's free here. So if I start from here and I go towards the inner part, I know where we're right. N equals 0, V equals 0, M equals 0. So this force totally goes to the left.
Okay, I have a question.
So that my point is, if you're insisting in knowing a priori the solution, you will get nowhere because it always depends on how the structure looks like. The only way to do that is to write equations. And this is one problem I faced since I started lecturing in structural mechanics, because people always ask me when there were nodes with hinges and there was a force applied, people ask me, can I assume that half goes to the right and half goes to the left? My answer was always, no, you don't have to assume nothing. You simply have to solve the equations to know which share goes to the left and which share goes to the right. That's my point.
I have a question. Is there a way in real life to see particles withstanding a load? Is there a way to test in a lab or something? If let's say I have a block of whatever, and I have a force on it, is there a way, I don't know, under a microscope or something, to see how the particles in real life are reacting to the
No way. That's what I said from the beginning when I introduced you the stress concept. I told you, stress is like God. There is in the book of structural mechanics, in the beginning chapter, it says, it is assumed that there exists a quantity which is called stress, which is defined in a certain way. Now, if you accept this model,
you have a choice.
everything follows. Now, of course, you have other choices.
Yeah.
There are different ways of assuming continua works. There are polar continuums, which work in a different way. Okay? Just to tell you, there is no stressometer. Every stress we assume in the lab is calculated. Okay? But as God, we have the proof of the existence of stress or the concept of stress, because when you sleep on pillows. You don't sleep on a needle. Okay? The load which has to be sustained is the weight of your head. But it makes a difference whether you lay on a pillow or you lay on a needle. And the difference is the stress.
Yes, but I do not come and assume like, oh, I'm lying on a mattress, but if I got my body on top of my stomach, the lower parts which are my leg don't have stress.
Because you're not interested in this case. But if you're designing a structure, you're interested in knowing which part of the structure bears which load. And this you achieve by writing the equations. In the same way, when you say, there are intuitive cases. When you say, okay, I have a balcony, okay? Suppose I have a balcony. I stand below the balcony. With my hand at the bottom of the balcony to help the balcony sustain the load. From intuition, how much of the load will be carried by the balcony and how much by myself?
Well, it depends. Did they build the balcony while you were there, or did you come after it was already built?
Now, let's suppose the balcony is unloaded. I place my hand and I load the balcony. How much of the load will be carried by the balcony and how much by myself?
How much force are you exerting afterwards?
As much as I can.
Okay, I'm assuming the answer is nothing.
Nothing on me, everything on the balcony. Yeah, that comes from intuition, but also from calculation. You can demonstrate the same by means of calculation. So in this case, intuition guides you in the right direction. In this case, it's more complicated. That's why I write equations.
I just feel like a lot of this is assumptions we make and then
No
so
assumptions.
our way to satisfy our own assumptions.
All the assumptions I make, for example, sign conventions, I always say, I'm assuming this, but it doesn't matter. Confirm. That's what I always say.
Yes, yes.
Tell me, Dani, or you wanted to give the answer? And you agree with her answer? How much force goes here? How much force goes here? Okay. We need just the right part of the structure, but piece of cake. So right part of the structure was HA equal to PL, and then VA or no 2PL, correct? Is it right that way? Okay, usual conventions plus tension, tension, clockwise, clockwise. So tension, N5, shear force, V5, and bending moment, I'm assuming it like this, M5. Okay? What do I get? This goes down, that goes down, so N5 equal to minus 2PL. V5 to the left, HA equal to PL to the right, PL. What about M5? If this is L, then M5 equal to PL squared. Okay? These are the basic equations. And then what I do is I add the second part, which is only L divided by 2. And again, PL, and this is 2PL. My sign conventions are tension, shear force is clockwise, and M, I don't need to put it, so I have tension, N6, shear force clockwise, not 4, 6, 6, 6, and then bending moment like this, M6, okay? So N to the left, PL to the right, N6 is equal to PL, V upwards, this downwards, V6 is equal to 2PL, then M6 is equal to what? This is clockwise with respect to this point, this is clockwise, so this will be negative, minus PL square, and PL square minus 2PL square.
Professor,
Yeah?
what do we put the
Hmm?
why didn't you do the irregular piece along without the vertical one attached to?
No, I didn't get it.
We put both numbers.
Yeah.
Why didn't we do this one and then that?
No, I started from here and then I go continuously here.
Oh.
Okay, so at the bottom, yeah?
So the concept of symmetry doesn't work with this structure.
Not at all. No, because of loads, because of restraints. Only the geometry of the member is symmetric. Everything else is not symmetric. So, we have an actual force, which is 2PL with the minus. And on the horizontal portion, it is PL with a plus. Okay? So it's continuous. Is it correct? Yes, because there is no shear force here. So there is nothing that can change the actual force. Okay? Tell me.
When you plot the negative sign of the shear force, can it be on the other side of the line?
As I said previously,
Sorry.
the important thing is that if on this half it's positive below, on the right side it's positive below, okay? So I shouldn't make positive, positive, below, and then above. Makes confusion. Although it's not strictly said incorrect. Simply it's confusing. This is done. Shear force on the top, PL positive. Horizontal part, 2PL positive. Bending moment. At the top it's 0, there is a hinge. At the bottom of the vertical part, it's PL squared tension to the left. So we start at this point with the same value. But at the end of this horizontal portion, it's minus 2PL squared, which I assume the tension at the bottom, in reality it's tension at the top, which means from PL squared to 2PL squared. Okay? Quite strange, the note here. What do we have from the horizontal portion? A moment that puts tension at the top. The value, PL squared. From the vertical portion below, a moment which puts tension to the left, whose value is PL squared. PL squared. What do we have coming from the right? A moment which puts tension at the top, whose value is 2PL squared. 2PL squared. Do you see that the node is in equilibrium? PL squared, 2PL squared. Look at the 2PL. Compression, right angle, it becomes shear, 2PL. Compression again, that's the flow. The flow of the force. Same for the shear. I pull here, negative. I get to this point, becomes actual force, shear force again. Okay? That's how our structure functions. Clearly not symmetric, as you see.
If there was a hand other part of it is not
Structure would be statically indeterminate and you could not solve it. By means of simple equilibrium equations. Besides, there is also the concentrated moment, the one we talked previously, which makes it non-symmetric. That's a non-symmetric action. Okay, I think we can wrap it up for today. I will be quite, wait a second. Okay, don't publish it on the social.
Like on the chat.
Yeah, okay, chat is okay.
There will be stickers, WhatsApp stickers of you within the night.
What?
There will be WhatsApp stickers of you within the night.
Okay, I will wrap it up for today, but also for the people at home, I am of course always available if you want to come and see me in the office, to come up with questions. I think the first call is, you know the date already? 17th of June, so there's still quite a month or so to prepare. So try to go through the practical classes. Did you download the WeBip material, Eriswaya? Did you? From WeBip, all the material which Maria Chiara so carefully and accurately produced for you. For you. You all. You all. Okay? There are people who didn't download the material until the day before the exam, correct? No, it wasn't you. No. You had it downloaded but not opened. You had?
I had it printed. Remember when Mona was asking you questions and she was showing you the sheets for my prints?
Did he? Prima, did he?
I downloaded something.
Something.
Yeah, I downloaded the song.
From WeBip or from the web in general?
No.
Movies, songs.
This thing, I downloaded the song exam equation. The things. Is this what you're trying to?
Yeah, basically all the material prepared by Maria
But
Chiara.
then someone told me there are notes or something. I don't know if I downloaded those.
There are also notes. There is everything.
The most recent that we did in February, is there a solution?
I think we solved it during one of our practical classes.
Yeah, I think it was the first one.
Yeah, but whose recording did not go well. But that's one occasion. Take the exam, solve it, and show it to me. Give it a try. Do you work in groups? Do you practice? Do you study in groups? It also works with structural design. Works, believe me. Okay, so for the time being, I have not planned to have other practical classes. Let's see how things unfold. I don't know. Okay?
Thank you for your
So,
time, Professor.
people at home, I will now stop the recording. See you. In case you want to come and see me, just write and we'll set up an appointment.